Recording.
Sure.
Always let me know. Thank you.
Yeah. No problem.
Always interrupt me if it's not being recorded because we want this on. So again, optics, how light and transparent materials or reflective materials will interact with that light. And again, what we talk about here, it also applies to ultraviolet and infrared for the most part. They're close enough in the spectrum that they have very, very similar properties. Okay, so what happens to an atom when we put it in an electric field? Well, it distorts. And what that means is, well, look at the classical sense. What it means is that electrical field can do work on the charges. And we know that work is adding energy or taking away energy. We can either put energy into the electrons that are orbiting the atom, or we can take it away. Okay. And basically, this energy comes in and out through photons of light. So, put something in an electric field, put an atom in an electric field, the nucleus is just too heavy. So normally we're affecting the electrons that are orbiting the nucleus. Okay, so right now I am wearing a red shirt, which absorbs mainly green and blue wavelengths of light. So when light comes in, puts a little electric field on the electrons, and if the electrons are at just the right energy, in quantum mechanics we say that there are different energy levels that the electrons can be at. If the distance between a lower energy level and an upper energy level is just right, say for blue light or for green light, then that atom is going to absorb that energy. Okay? So absorption is a very important process in optics. Again, looking at your clothing, what color your clothing in really determines, what kind of atoms are in there that are responsible for giving it the color. We normally put, dyes in our clothing. If they have just the right energy spacing, they will absorb certain colors of light. So my red shirt absorbs mainly blue and green light. We can also have atoms give off light. And of course, we think about, making an atom excited. I'm looking at my television screen, my computer screen, and behind the computer screen are a bunch of white LEDs. And what happens here is the atoms in the LEDs are semiconductors. We'll put electricity into the LEDs. That'll give the atoms energy, causing the electrons to jump up to a higher energy level. And then once they're up there, well, they like to drop down to the ground state. And what do? They give off some of that energy as a photon. So absorption and emission are one of the two most important properties or interactions that light can make with atoms. We can, absorb light. In that case, we convert light into another form of energy, or we can emit light where we take something energetic. Usually we use electricity to make the atoms energized. And then the electrons of the atoms will go from their energized level, dropping to a lower level. Okay. Here are some examples of vapor discharge lamps. These are very efficient lights, but they also, produce quite a bit of light. This is a sodium light at the top. I wrote Na because that's the chemical symbol for sodium. There, in a quartz tube, we put sodium, send electricity through it. The electricity bumps those electrons up to an upper level, and then the sodium atoms will then drop. Well, the electrons will drop from the upper level to a lower level. It gives this very distinct orange color. Anytime you see a street light and it's orange, that's a sodium lamp. Okay. Down here, this is what's called a metal halide lamp. Okay. It has a mixtures of different metals. It has mercury in there. I think it also includes halogens, not quite sure which halogens it includes, metal halide. That type, typically the metal halide will give sort of a bluish white color there. So again, emitting light is just a matter of getting the right energy to the right atoms. If you get the right atom, okay, it'll have a energy difference in its lower and upper states. The electrons will be able to jump just the right distance to give off the color that you want. If you want orange light, put energy through sodium vapor. If you want bluish white light, well, that's the metal halide light, which is also a very common type of street light or floodlight that we use. All of these are being replaced with LED lamps, just because the LED lamps last longer and are slightly more efficient. Okay, so light can be absorbed by atoms, light can be emitted by atoms. But when I'm looking at the room around me, I am seeing different objects because the light is bouncing off those objects and then returning to my eye, okay? That's a process that we call reflection. And reflection, there's no energy loss. The photon just comes in, bounces off the atom, and goes out. There's a whole quantum mechanical explanation for this that I don't want to go into. But normally, if an atom doesn't have a resonance, it doesn't have energy levels that correspond to that space, it'll just bounce off the atom. Now, the red shirt, the dyes in my shirt, don't have a resonance in the red. So the red light comes in, bounces off of it. You see the red light, coming to my camera and then transmitted over the internet. So you say, oh, okay, he's wearing a red shirt. Probably getting tired of me talking about red shirts. Absorption, emission, reflection. The last category of the way light interacts with matter is refraction. Now, for emission, absorption, and reflection, we don't need to have a transparent material. Refraction is kind of special. Oops. Hey, I wanted my box tool to come up. There it goes. Refraction is typically reserved for transparent materials. And with refraction, we actually change the direction of the light by slowing it down. Refraction is a process. Now, this is a little bit difficult to follow. But if you think about the light waves as being these ripples going through space, coming in, coming in, coming in. If we can slow down the light, okay, and cause it to go at a lower velocity, it will actually slow down this side first, okay, and then slow down this blue side last. So if I'm slowing down the part to sort of the lower left, that turns the direction that the wave is traveling. And now we see that our refracted wave travels slightly different, in a different direction than our initial wave, okay? What you need to know about refraction? Well, again, if you do the thought experiment with this and try to understand how the wavefronts are going, you can understand the change in direction. But I think it's more important for you to understand that refraction is basically two things. It's the change in speed of light. Yes, light normally travels at 3.00 times 10 to the 8 meters per second, what we normally call c. But we can also slow it down where the new speed is less than c. Like, for instance, in water, it travels about 33% slower. In glass, it travels about 1/4 slower. Glass about 1/3 slower. But by slowing down the light, we're also bending the light. Okay, little bit hard because it's not as intuitive as I'm trying to make it sound here. The last process we'll talk about is this idea of fluorescence. Go back to my white LED, which is lighting up my computer screen right now. Basically, when you look at a display, there's the white LEDs behind it, and then there's an LCD screen in front of it, and the LCD screen will basically select what light makes it through and what light is not permitted to go through. So these white LEDs actually have two components. They have an LED which produces light, usually blue or purple light, and then they have a coating or a fluorescent material, phosphorescent material, which changes the color. So for instance, I want to produce white light, okay? Problem is the LEDs that I have, they naturally produce blue or even violet light. So we use a fluorescent material. The name of this fluorescent material is called cerium oxide, and they usually put some other materials in there too. And the bluish light comes in, okay? That's from our blue LED. It hits this material, and then what comes out, because this material has many different resonances, is we get some blue light out, okay? So not all the material, not all the light is absorbed. We get some green light out, and we get some red light out. So this fluorescence takes shorter wavelengths of light, and purple and blue are shorter, and it allows us to produce new colors that weren't originally there. Okay, so white light is all colors, and what the fluorescent material does, if we choose just the right fluorescent material, it will essentially produce all the colors in the spectrum. We get white light out. So the old fluorescent bulbs, they used to use mercury vapor. They were mercury vapor discharge lamps. We don't like mercury because it's toxic. It's not good for the environment. That would produce ultraviolet light, and then we'd coat the tubes of the fluorescent tubes with, again, different types of materials, like cerium oxide is one of them that I talked about. They used to use phosphor. That's where the term phosphorescence came from. But there are a lot of different exotic materials that they can use to create this fluorescence. If you've ever worn fluorescent clothing, like right now it's hunting season up by me, so I wear fluorescent yellow whenever I'm out running or something. What that does is it takes the ultraviolet light from the sun and it re-emits that as new colors, and that's why it looks like it's glowing. It's like, where's this light coming from? It's like day glow. Well, it's converting the ultraviolet light from the sun into new colors, okay, which your eye can see more easily. So it looks brighter than it should, but that's day glow. Black light. Does anybody know what black lights are? Black lights aren't really black. What are black lights?
Isn't that UV light?
It is UV lights, near UV light. And if you wear day glow clothing, you're wearing material with fluorescent dye, and it will glow. It'll turn the UV into visible colors that we can see. So that's kind of a cool effect because your eye can't really see the UV very well. But the visible colors that it fluoresces at, produces some really interesting effects. I mean, if you look at black lights, you're like, well, it's not really black. It's sort of got the purplish glow to it. But it's near ultraviolet, so your eye can just sort of sense it. We say ultraviolet's invisible to the eye, but a little bit does make it through. So, oops. I let somebody in, so I got to click on this again. So if the frequency of the electromagnetic waves are a good match, they will absorb the light. So for instance, photosynthesis. Photosynthesis happened originally in the ocean, where mainly blue light would make it to the layers where the cyanobacteria was. So, nature's great at using the same thing over and over again. So naturally, chlorophyll, which is the pigment for photosynthesis, strongly absorbs blue light, okay? But it also has a comparable resonance where it will absorb red light, okay? Why do plants appear to be green? Well, plants appear to be green because the green light doesn't have a resonance with the photosynthesis molecule. So the photosynthesis molecule is very good at absorbing energy from blue light, very good for absorbing energy from red light. It doesn't do so well with green light. So that's why plants appear to be green. If plants were, super, super efficient, they would actually be able to convert all light into energy. And that, of course, would make them black. They wouldn't reflect any light. But, the sun's bright enough, they don't need all the energy there. So when the photosynthesis molecule evolved, plants just passed it down to succeeding generation. And that's why we now have green plants.
Is it because green is in the middle, they like to absorb the green light?
Well, I'm not a biologist, but what I understand is it was when the molecule first came up, it was either that it was good at absorbing red light or blue light, and then it picked up the other color just due to a slight modification. It's a way things are. Plants. Oh, you just taught photosynthesis. Cool. Maybe you can tell us a little bit about the color selectivity. Not being a biologist, I took micro and molecular. Chlorophyll A and B absorb blue and purple the best. Okay, so originally light propagates better through water. So blue was the original color that it was trying to convert into energy. And due to a quirk of resonance, it picked up nearly 1/2 the energy. So anyway, yeah, exactly. They don't absorb green well. That's why they reflect it. Now, some plants actually have other pigments beyond chlorophyll. Keratin is a very good example of a molecule that will absorb things like green light. Keratin doesn't have strong resonances in the orange and red. That's why you get those colors. It does absorb blue and green light well. And I want to say the xylene, 1985 was when I took my last biology course. So you can see my knowledge is a little bit out of date there. But in any case, oh, we have 5 minutes, so I got to finish up this. But yeah, I mean, it's so interesting. I always enjoyed the micro and molecular biology because it really had some neat applications with regard to chemistry and physics. You really got to see, on a microscopic level, what was going on. So fun stuff, but I went off in a different direction. Solar energy, we're all aware of solar energy as being a renewable source. And recently, it's the cost of it is really coming down. If we think about it, going back to photosynthesis and plant energy, the original source of energy powering plants, of course, was solar energy. And the fossil fuels that we see today, crude oil is really plankton that has been fossilized. Coal is really, plants that were on the land that were fossilized. They got their energy from photosynthesis, which got its energy from the sun. Really, all the different types of sources of energy, geothermal and nuclear are the only ones that don't have their origin going back to the sun. So we are finding that we want to reduce our carbon footprint. So there are many different ways we can utilize energy from the sun to achieve this. Passive solar heating, we just let the energy through the windows and let it heat our house. Solar water heating, this is very popular in parts of the world where you don't have a lot of cloudiness. And photovoltaic cells, which are just becoming so inexpensive that they are really helping power the grid. And again, passive solar heat, we talked about earlier how windows are bad because they let heat out. But if windows are engineered just the right way, we can get the sunlight into buildings, because during the winter time where we want the heat, it comes in at a lower angle, where during the summertime, it's at a steeper angle. If we face these windows toward the south, we can really, passively just let the sun manage the heat inside our buildings and our house. Solar hot water, again, is very, very popular in lower latitudes, in areas where there's tons of sunlight. In the Northeast, they're a little bit difficult because of the cold temperatures. You got to put antifreeze in them. There's not so much sunlight, so they're sort of not cost effective. But the neat thing about solar hot water is you can use it to not just heat up your domestic hot water, not just use it to heat up your house. You can actually use these to power air conditioners. There is an ammonia cycle air conditioner, which is commonly used in RVs, which can simply be powered by solar hot water. This is the weirdest thing in the world. But thermodynamically, you can play this trick where you use the solar energy to heat the refrigerant, causing it to expand beyond where it would normally be. And then when you allow it to be reabsorbed, it cools down. So, you heat something up to cool it down is really the strangest thing, but it's possible. And of course, solar hot water, we can use to heat our hot water, even our house. But really the biggest breakthrough are with photovoltaic cells. These things are becoming so cheap and are really helping power the grid. The biggest problem we face right now is, although photovoltaics are one of the cheapest forms of energy now, it only works when the sun shines. So these solar cells, really inexpensive now. But what do we do at night when we want to store the energy? That's where the cost becomes prohibitive for many homes. Okay, so the idea now is we just dump the energy onto the grid, and when we need it, we pull it back off the grid. But getting people completely off the grid just using solar cells, good luck at night. Again, the cost for storage is what's really high. And here's a map of where solar energy really does well. Oops, let me change this. Here we see this red out here, where you really get a lot of sunshine, and you can easily convert that energy into something usable like electricity or heat. We're not that great up in the Northeast, but again, with solar hot water doesn't work so well. However, photovoltaics being cheap enough, they can help the grid out there. And of course, if you're up in space, not much choice. You have two choices. You can either use nuclear power, which is not something you want falling back to Earth. You don't want a nuclear reactor landing on somebody. Or you can use solar power, okay? And again, here is the current cost of solar power in comparison to other things. And again, nuclear is very expensive. We can use natural gas turbines to supplement the grid when we need that extra electricity. But typically, natural gas is pretty competitive. But again, what do we do when the sun's not out? Yes, it's cheap, okay? And one of the things that the power company is doing now is they're using solar when the sun is out, and then when they need extra electricity, they'll switch to natural gas turbines to make up for the lack of sunlight. Again, wind has sort of the same problem. It's great when it's there, not so good when it's not. Okay, folks, so that's it for today. I'm going to stop. I'm going to find it.